Returning to characteristics of remotely sensed images, we have talked about spatial resolution, and we have talked about radiometric resolution. We're now going to talk about spectral and temporal resolution. So spectral resolution is the number of spectral bands. In this case, I'm showing 3, each of which is an array of values for a specific portion of the electromagnetic spectrum of either reflected light or emitted heat that's been recorded. Remember that images can also contain some other user-defined information created by combining or enhancing the original bands or new bands from other sources, for instance, a DEM. Strictly for remote sensing, we're concerned with spectral bands at this point. To give you a sense for what different bands look like with different spectral characteristics, here I'm showing you a black and white visible panchromatic scene and an infrared panchromatic scene. So in both cases, they're one-band images. In the case of the left, you're looking at integrated light from across the visible, which is what people generally call a black and white image. On the right, you're looking at energy recorded from the infrared portion of the spectrum, the near infrared specifically. And in the center of the image, you're looking at 2 areas that are forested. On the left, you've just got a sort of a uniformly dark area because forests absorb most visible light. But at the image at right, the forest is not only generally brighter, but there's a deciduous component that are even brighter than the overall forest. Okay, and if you look, you can see there's a especially good example where there's the deciduous vegetation is associated with a stream there, some kind of water course. And as we've discussed, broadleaf deciduous vegetation is brighter in the near infrared than is conifer needleleaf vegetation. So it shows up brighter on an image. So here's another example, where you have multispectral data, okay? And this is what you see most commonly when you're looking at airborne and spaceborne platforms. There aren't a lot of contexts in which collecting just a single band makes sense. So generally, multispectral sensors are going to be collecting in the visible, the near infrared, and the mid or shortwave infrared, and then some of them also collect in the thermal infrared. The thermal infrared requires a different sensing technology, and so sometimes it's left off. And as I've said before, the nice thing about multispectral data is you can reassign the various bands, whether or not you would be able to see that kind of light with your eyes, reassign those bands to the bands that you can see, red, green, and blue, and see different combinations of light that you can be very flexible with. You can change their order, you can change the color assignment to make things easier to see. So as an example, Landsat 7 has 8 bands of spectral resolution. And you can see those in all except the lower right image. And the thing to note is that the pattern of tone, brightness and darkness, differs as a function of which band you're looking at. And some areas are going to look very similar. So for instance, this is a coastal scene, and there is this arching feature that sort of starts at the bottom of the image and then goes up to what appears to be a small island. That looks pretty similar in all of the images. It's probably sand, and so sand is bright in all parts of the spectrum. So fair enough. Other areas vary, and so that's a function of the spectral signatures for those other land cover types. In the bottom right is a blow up of one of the bands, which is the panchromatic band. It's shown in large because the panchromatic band is of higher resolution than the other bands in the image. Landsat has a spatial resolution of 30 meters, and the panchromatic band has a resolution of 15 meters. When you're thinking about spectral bands, again, you need to go back into this full context, starting from, what are the colors invisible, where those are located, with respect to the wavelength, the near infrared, the mid infrared. Here I'm not showing thermal. You need to think about it in terms of how much energy there is, the exo-atmospheric spectral irradiance, which just means the brightness, that red line, the brightness of the sun's energy as it reaches the top of the atmosphere, i.e. without atmospheric interference. That cyan line, which is atmospheric transmittance, and shows where you're going to be able to get good observations of the surface. You need to think about it in terms of that next window down, which is the various kinds of spectra that you're interested, or land cover types that you're interested in sensing. And then we get down to 4 popular sensors or sensor types. Some of these represent more general sensor types like QBIRD, that's QuickBird. It's a high spatial resolution system. And those systems, so that's, I do not recall at the moment what QuickBird resolution is, but it's less than 2 meters spatial resolution. QuickBird has a blue, a green, a red, and a near infrared. That entire class of sensors is similar in those are the bands you're going to see. Thematic Mapper has those same 4 bands and 2 mid-infrared bands. So that allows you to bring in analysis, for instance, of water absorption. MODIS, this is a sensor that differs from TM in that TM has a pixel resolution of about 30 meters. MODIS has varying pixel resolutions from 250 to 1,000 meters. And in fact, I'm sorry, there are atmospheric bands that are even coarser. But for our purposes, it's between 250 and 1,000 meters, and similar bands to TM. There's an extra near infrared band there, but very similar to Landsat, but with coarser resolution pixels. And then there's Avaris at the bottom, and Avaris is a hyperspectral or imaging spectrometer system. And rather than having bands which have been selected for optimal placement within, the range of wavelengths, this is a system that records radiances, brightnesses within many narrow adjacent bands. So Avaris has 242 bands, and they are spaced out every 10 nanometers. So, and that's the old Avaris. The newer Avaris has twice as many bands, and they're 5 nanometers wide. So, um, you're sort of doing an exhaustive sampling of the reflectance pattern. And this is the concept. So each pixel or spatial element has a continuous spectrum that you can use to analyze the surface and the atmosphere. These systems were based off the concept of spectroscopy as it's used within geology to identify different rock types. So essentially, you're getting the information that a spectroscope would give you, um, but it's giving it for every pixel across the landscape. And so, if you're just observing the atmosphere, you would get something like the top of those 4 graphs. That would just be transmittance. For soil, you're going to get similar pattern, but you can see that actually as you go further out past the shortwave, into the shortwave infrared, you get in this soil a lower reflectance. Here's a curve for water, and finally the very should be familiar to you now, the curve for vegetation. And they often show this data as a data cube. You can't observe more than 3 bands at a time, but you can put together this sort of data cube figure where you've taken an image, you're showing the top of it in a 3-band combination. That should be familiar to you as looking like a color infrared um, combination. And then along the edges, the the radiance, the brightness of each pixel is shown in a pseudocolor lookup type. So as you go for each pixel traveling downward, you're looking at the reflectance or radiance as a function of wavelength. So for instance, areas of vegetation, you can see along the left edge, there are places where the pixel at the edge is vegetation, and you can see low values in the visible, higher values in the near infrared, some high values in the mid infrared, and then going further down as you go up in wavelength. So that's a data cube. We can look at spectral and spatial resolution using a graph like this so that you can sort of visualize the characteristics of different sensors and identify some classes. So on the x-axis is GSI, that's basically pixel resolution. And the y-axis is the number of spectral bands. Each one of those dots is a sensor. It can also be, for instance, a subset. So panchromatic bands are, for instance, plotted for the same sensor at as well as the visible and near infrared bands. So when you have a sensor that has more than one resolution, it's actually plotted in 2 places. You can see that along the left-hand edge where you've got QuickBird panchromatic, which is a 1 meter spatial, I'm sorry, it's a 75 centimeter spatial resolution. And then just above it, there's QuickBird VNIR, that's visible and near infrared. And in that case, you're looking at a 4-band system that's 3.3 meters or something similar. And you can break these sensors down into 4 classes. At the top, we have the hyperspectral sensors, which I was just discussing. So Avaris Hyperion, which is a 30-meter resolution satellite version of Avaris, and HIMAP, another airborne system. To the left, along the bottom, you have hyperspatial or high spectral resolution multispectral sensors. And these include, there's a wide range of these days. So QuickBird, Iconos, Worldview, a number of these. And those generally are similar in the sense that they have high spatial resolution, panchromatic under a meter, multispectral on the same sensor, less than 4 meters. And they have similar applications where you really need to get a high spatial resolution, for instance, for urban planning, where you want to be able to see individual features. The next class over is regional multispectral sensors. So this includes things like the Landsat suite of sensors that includes Enhanced Thematic Mapper Plus, so ETM Plus, MSS, Multispectral Scanner, and Thematic Mapper should be in there, but I don't see it. So these are sensors that have, between, generally 1 and 12 bands maximum, and spatial resolutions of between, 4 and 150 meters. So these are useful for regional scale analyses. So for instance, Landsat, sort of the most popular sensor out there, especially for historic analysis, because the program's been around since 1972. Those are a spatial resolution of about 30 meters, and they cover an area 185 kilometers by 185 kilometers. So those tend to be a good scale for mapping, sort of at anything from the local domain, like say if you wanted to map Rocky Mountain National Park, mapping just land cover, you're not interested in objects, these kinds of sensors would be a good option. All the way up to say, you can do national scale analyses, but it's much more convenient to be looking at sort of a state scale. And there have been national scale mapping projects using Landsat, but those tend to be very large projects. And then on the right, you have the sort of the global multispectral sensors. Okay, so these are systems that have, pixels that are maybe 250 meters spatial resolution through a kilometer spatial resolution, and between 2 and 20 or 30 bands. And these are coarse spatial resolution. Okay, so in general, you're not using spatial information when you're doing these analyses. You're using spectral information, and so they tend to have more spectral bands so that you can make whatever determinations you need to make using just the spectral bands. As I've discussed before in brief, numerous sensors have both high and low spatial resolution bands. So these high spatial resolution sensors, QuickBird, Iconos, and Worldview, they all have 4 multispectral bands at 1 resolution and 1 panchromatic band at 1/4 that resolution. So the original sensor of this type was Iconos, and it had 4-meter um, multispectral spatial resolution and 1-meter panchromatic spatial resolution. And the reason you have 2 bands, I mean, obviously it's because you can get that higher spatial resolution, is that, the reason you can do that is that the panchromatic band samples over a wider range of wavelengths, right? So the multispectral bands might have widths of, I'm just going to throw out a number, 50 nanometers, whereas the panchromatic band is going to be sampling over, say, 300 nanometers. And that just means that the sensor for the panchromatic bands is collecting more energy than any of the multispectral bands. And so it's possible to have higher spatial resolution. Now, other examples here, I've got Landsat 7 has multispectral bands at 30 meters and that 15-meter panchromatic band as well. MODIS, the terrestrial bands, that is the bands that are meant for predominantly sampling of the terrestrial surface, those are mostly 500 meters, but red and near infrared is those are available at 250 meters, and that's so that you can calculate vegetation indices at that higher spatial resolution. There is a process called pan sharpening, and that's illustrated down there at the lower right, which allows you to combine these bands, the high spatial resolution or higher spatial resolution panchromatic, and then the multispectral bands, to give you a new image, that one on the right, that appears to have the higher spatial resolution, but also retains the multispectral data. And that works visually. It does not work as well, certainly, for spectral analyses when you're doing statistical analysis, for instance, of those pan-sharpened bands. And then we talk about radiometric resolution. So these are the number of values that we can record for an image. The more values you can record, the larger the the better distinctions you can make from various shades of gray. So once again, I'm showing you one of the bands from that Lotus image, and then to the right of the image, I'm showing you a grayscale. And that grayscale basically just goes from 0 to the maximum value that you can get with each one of those values, and it allows you to see whether or not you can get sort of continuous, you can see continuous differences in the image. So the 8-bit image, that's 256 values, and you can see next to the Lotus that grayscale indicator looks very smooth to us. That's because our eyes can generally pull out 110 grayscale levels. So anything more than that, you're going to see is smooth. The next one over to the right shows 6-bit values, 64 values, and once again, the what we would call a grayscale wedge, the range of grayscale values from darkest to brightest, that looks pretty continuous. You can kind of see some sort of well, I think I can see different jumps between certain levels, but it's not dramatic. You go down to 4-bit data, that's 16 values, and you can definitely see in that grayscale wedge where it's jumping from one to another, And the image itself, the lotus itself, you can't see the finer distinctions between different shades of brightness or darkness. And then finally, I just show you 2-bit data, which is 4 values, just to give you the sense of this is where it goes. All of a sudden, you can't even tell where the leaf color is from the background color. So 8-bit data, Landsat, well, Landsat, the Landsat program has had 3 major kinds of sensors. The multispectral scanner, which was put on the first Landsats, that was replaced by the thematic mapper series of sensors. And now we have the OLI sensors. And MSS, the first one, had 6-bit values, so that's relatively coarse. We would consider that. The thematic mapper series had 8-bit, and the OLI, I believe, is 16-bit. So we're getting higher and higher quality data, making it possible to differentiate between smaller and smaller differences in brightness. So this gives you an example. It's better to have the distinction between various levels of brightness, but the more levels of brightness you have, the larger the file size. So MODIS data is coarse spatial resolution. We're just going to call it 500-meter resolution here for our purposes. There are 400 pixels in a 10 kilometer by 10 kilometer image. The radiometric resolution is 16 bits, which is 2 bytes. I'm trying to avoid getting into the technical discussion of what bits and bytes are, but it's the amount of memory taken by one observation or one pixel. It's got 8 bands, and so for a 10 kilometer by 10 kilometer area, it's 0.006 megabytes, so it's 6K. Very small. Landsat, 25 meters, you can call it, it's very often resampled. It's 30-meter data fundamentally, but it's very often resampled to 25 meters because it's a nice number to work with. So there are 160,000 pixels in a 10 kilometer by 10 kilometer image. Radiometric resolution is 8 bits. There are 6 bands, not excluding the thermal band for these purposes. And so that's like 1 megabyte per 10 kilometer by 10 kilometer image. If you look at ICONOS, just the multispectral data, that's 4-meter data. So there are 6,250,000 pixels in a 10 kilometer by 10 kilometer image. The radiometric resolution there is 11 bytes, which is kind of a weird number, but they're just trying to keep the images as small as possible. 4 bands, and so each 10 kilometer by 10 kilometer area has about 32 megabytes. Of course, we're not sampling 10 kilometer by 10 kilometers images, okay? We are generally sampling much larger areas, with the exception of ICONOS, which a single scene is about 11 by 11 kilometers. So these sizes get much bigger. They probably don't sound that big to you because storage has become so inexpensive, but a whole Landsat image is about 350 megabytes, one of the Landsat thematic mappers. When I was starting out in remote sensing, well, let's skip ahead. When I started my first professional position in remote sensing, I thought the lab that I moved into was just at the cutting edge because there were 500 megabyte hard drives. So 500 megabytes, that's half a gigabyte. And I challenge you to find a USB stick that's, 1 gigabyte anymore. it's, now they're 32 gigabytes. So, right, the size of these images becomes more and more workable, obviously, as memory and storage goes down in cost. Okay, so now temporal resolution. Big factor with temporal resolution is the orbit that the satellite's in. We have two kinds of orbits. We have a geostationary orbit. So that means that the sensor is in an orbit where it is constantly above the same point on Earth. And then we have a near polar orbit. And so that is a sensor that's making a pass that passes, within a few degrees of the two poles, okay? And as it is going down the descending portion of the orbit, the Earth is moving beneath it. So it actually winds up covering the entire Earth. Let's look at what that means. So the Landsat orbit is inclined. That is, you could sort of imagine an orbit that just went purely north-south, but this is actually inclined. It's about 14 degrees. And this sort of orbit passes the equator at the same time locally. So when it's passing the equator, the point underneath the equator is has the same time. It's like 9:47 a.m. For a particular observation. Okay, and Landsat 7, or most of the Landsats, revisits a scene every 16 days. Okay. MODIS actually it says twice a day. There are two MODIS satellites. Each one samples the entire Earth once per day. So one thing to keep in mind when you're looking at Landsat data in particular is we identify images by their path and their row. So the row is north-south, the path is east-west. And so as the satellite is descending, it's going through rows right after each other. In fact, the rows are just done continually. We break them up into images later, but the measurement is fundamentally continuous because it's not a frame capture system. But then you have to wait until the next day to get the following path. Okay, so it has to inscribe all of the paths around the Earth until the Earth returns to that next path. And you can see that in the lower left. So, you have orbit 1, day 1, being captured first. And that goes down in this case, around, Western Florida. Orbit 16, I'm sorry, orbit 2 on day 1, okay, is out where we are, Colorado or Utah, okay. Orbit 15 occurs on day 2 and is immediately next to orbit 1 for day 1. And then orbit 16 on day 2 is immediately west of that first excuse me, orbit that came down through Colorado or Utah. So it has a 16-day repeat cycle because it's going to be 16 days before orbit 1, day 1, is recaptured. And just to give you a sense of how temporal resolution is important, this is some information that was derived from Landsat images for the Pacific Northwest. these are harvest dates for that area. Okay, so on the right you can see we're looking at Western Oregon and the Cascades as well. So it's the Coast Range and Cascades of Oregon. The way that harvest is mapped, in the upper left hand corner, you see three images. These are what are known as tassel-capped images. We will talk about this later. All you really need to know at this point is that blue is forest and red are clear cuts. And what you can see in this area is in 1988, there's only like 3 clear-cut patches. In 1991, down one panel there are more clear cuts, but they're not a large part fractionally of the landscape. By 1995, a large area of this subset has been clear cut. Because the blue areas and the red areas are so distinct, it's very easy to come up with a classification that allows you to say, oh, something was harvested between 88 and 91, or something was harvested between 91 and 95, and then combine those in a GIS to give you that yellow and cyan map. And the nice thing about this is if you look on the right, we've got all of Western Oregon mapped for forest dates. This was back in like 2002, so they'd done between 72 and 2000. This is kept up to date, so this now exists through presumably 2018 or 2019. If you look, there's a magnification, and there's a little reservoir there in dark blue, and then various patches that are keyed out in that legend above it. What you see is toward the west of that patch, we have very large clear cuts that are that account for most of the landscape. To the east, we have much smaller clear cuts and a lower percentage of the landscape that's been clear cut. And the difference is that somewhere within there, we go from private land to public land. And so the public land has more restrictions. So the reason this relates to thematic mapper temporal resolution is that even though you're collecting images every 16 days, not every image is worthwhile. In the Pacific Northwest, most of the year, you're just going to be looking at clouds. And so you really need to have higher collection frequencies to make sure you get a handful of good images every year. And the same is true in the Amazon. During the wet season, it's very difficult to get a good-looking image. Most of the good-looking images are from the dry season, as you might expect.